On November 3rd, 1973, a massive rocket stood on the pad at Cape Canaveral. It was carrying a small but vital passenger named Mariner 10. Primary mission required flying toward the sun to study the planet Mercury. However, during its long journey, this craft achieved something that no other ship had ever attempted. It became the first true sailor of the stars. Most people think that space travel requires massive engines and heavy fire. But Mariner 10 showed us a different way. It did not just rely on chemical propulsion or the gravitational pull of planets. It became the first spacecraft to use the solar wind as a tool. Utilizing the stellar stream, the probe navigated the vast, dark void of our planetary system. This marked the practical birth of a concept that sounds like science fiction. This is the story of the solar sail. What exactly is a solar sail? To understand it, you must imagine a ship in the middle of a vast ocean. But this is not an environment made of water. It is the silent vacuum of space. On Earth, wind hits the fabric of a sail to push a boat. In space, there is no air, but there is light. This radiation comes from the sun in a constant stream of particles and energy. This light creates a real, physical pressure. This subtle thrust can push a spacecraft forward just like wind. Back in the 1970s, the team behind Mariner 10 had a clever idea. They used the solar panels of the probe like makeshift rudders. By tilting these wings, they could control the position of the craft. This maneuver became necessary because the probe was diving deep into intense stellar radiation. This trick worked perfectly. It allowed the probe to send back over 4,000 photos of Venus. It revealed details that had remained hidden from the human eye for centuries. The brave little sailor eventually reached Mercury. It mapped 40% of the planet's cratered surface. At its closest point, it was only 300 kilometers from the ground. None of this would have been possible without architectural ingenuity. Craft was equipped with two massive solar panels. They stretched 8 meters wide. These surfaces were not just for collecting power. They served as the wings that allowed the probe to lean into the light. There is a simple rule of physics at play here. The larger the surface of your sail, the more light you can catch. The more light you catch, the more momentum is transferred to your ship. It is a perfect cosmic analogy to a traditional sailboat. But out here, the wind is made of photons. These tiny particles of radiation are the key to moving across the galaxy. In traditional rocket science, there is a cruel and inescapable paradox. To go further into space, you need more propellant, but chemical fuel is heavy. This mass adds its own weight that must be lifted. The more weight you add to your tank, the heavier the spacecraft becomes. And the heavier it becomes, the more energy you need just to move the payload you just added. It is a cycle that limits how fast we can go. On a standard mission, we can only carry a tiny amount of propellant. Every extra kilogram is a massive burden during the launch. Solar sails break this cycle completely. They offer a free source of propulsion that never runs out. Instead of carrying a heavy engine and tons of chemicals, you simply unfurl a giant sheet and wait. You let the sun do the heavy lifting for you. But for this free lunch to work, the physics must be perfect. Pressure from sunlight is incredibly weak. It is a gentle and constant nudge. It is not like a violent explosion of a rocket motor. Because that push is so small, the sail itself must be impossibly light. Think about the sails used on ships here on Earth. If we took that same heavy fabric into space, it would be useless. The weight of the material would be so great that the light would not move it. The sail would be its own anchor. It would hold the ship back instead of pushing it forward. This is why modern solar sails are a masterpiece of material science. They are made of advanced polymers. These are ultra-thin plastics. They are lighter than a feather. They are much thinner than a human hair. But being thin is not the only requirement. To get the maximum kick from the sun, the surface needs to be highly reflective. There is a fascinating trick in physics happening here. Imagine a single photon hitting a surface. If that surface is dark, it absorbs the particle. This gives the sail a single push of momentum. But if the surface is a perfect mirror, the light hits it and then bounces back. According to the laws of motion, that reflection transfers twice the momentum to the sail. It is a double push for the same amount of light. Engineers coat these thin films with a metallic mirror-like finish. This doubles the efficiency of the sun's energy. It is the difference between catching a ball and having it bounce off your hand. The bounce gives you the stronger shove. Even with this double push, acceleration takes time. A solar sail does not blast off like a rocket from a pad. It starts very slowly. At first, the movement is almost impossible to see. However, because that pressure never stops, the speed builds up. The sun never stops shining in space. That tiny acceleration accumulates over weeks and months. Eventually, this cumulative effect can change an entire orbit. It can send a probe screaming toward the outer planets. It can reach speeds that no chemical rocket could ever maintain. Creating a sail that is massive yet light is an engineering nightmare. The larger the sail, the more light it catches. But the higher the risk of failure becomes. A single tear can ruin the entire mission. Even with perfect material, there is a physical problem. How do you get a sail the size of a tennis court into space? You cannot fly a giant, delicate sheet through the atmosphere. It would shred into a million pieces. This is where space architecture turns into cosmic origami. Engineers must take these massive surfaces and pack them into a small volume. They must fit inside a standard rocket. This is a masterpiece of precision. The material is so fragile that every fold must be perfect. It cannot rub or tear during the violent launch. Once the craft reaches the silence of orbit, the real magic happens. The sail has to unfurl slowly. It opens up like a flower on the water. If one corner snags, the mission is over. If a single wire tangles, millions of dollars are lost. We saw a version of this challenge with the James Webb Space Telescope. Its sunshield is not a sail, but it uses the same idea. It is a massive reflective umbrella that had to be folded and stretched perfectly in the void. True pioneer of this technology was a mission called Icaros. It was the first spacecraft to use a full-scale solar sail. It proved to the world that light could steer a craft. Shortly after, NASA followed with a project called NanoSail D2. This was a tiny satellite that successfully opened its sail in orbit. It spent 240 days sailing around Earth using only the pressure of light. When its mission ended, it performed one final maneuver. It used its reflective wing to catch the upper atmosphere. It burned up like a falling star. These missions showed us that the sailor model works. We have learned how to pack, launch, and unfold these silver wings. But as impressive as the sun is, it has its limits. Its light is constant, but it is not concentrated. If we want to go faster, we need more power. If we want to reach the stars in a single lifetime, we cannot wait for the sun. We might need to stop waiting for the natural wind and start building our own. This is where the vision of Professor Igor Bargatin comes in. He is a researcher from the University of Pennsylvania. He has proposed a radical shift in how we think about sailing. His research focuses on sails driven by high-intensity light. Specifically, he suggests using massive Earth-based or orbital laser arrays. To understand why this is a game-changer, think about a common laser pointer. A small device concentrates its light onto a tiny dot. On that tiny surface, the intensity is very high. Now imagine scaling that technology up to an industrial level. By condensing a beam of light into a powerful stream, we can blast a sail with energy. This provides far more force than natural sunlight ever could. It is the difference between a falling leaf and a jet engine. If we point a high-power emitter at a sail in the void, we can provide a constant and heavy thrust. This could accelerate a probe to incredible speeds. These are speeds that could make interstellar travel a reality for us. There is a major trade-off to consider. Sunlight is free. It is a natural and infinite resource that just exists. A directional light system is a massive investment. You have to generate all of that energy. You have to power the emitters and keep the beam focused. The target is moving away at thousands of miles per hour. It is no longer a free ride. It is a high-tech powerhouse. To make this vision efficient, we must move the emitters into space. If we fire them from the ground, our thick atmosphere scatters the energy. It wastes the power of the beam. But in the vacuum of orbit, there is nothing to stand in the way. A focused beam in space can stay sharp across millions of miles. It can push our silver wings further than we ever dreamed. We still have a long road of engineering ahead. Many technologies are left to perfect, but the math is very clear. By combining solar sails with human energy, we are turning the galaxy into an ocean. We have come a long way since that morning in 1973. Mariner 10 proved we could navigate the void using the pressure of stars. What began as a clever trick to save fuel has evolved. It is now a roadmap for our future as a multistellar species. We are no longer just looking at the planets in our backyard. We are looking at the massive gaps between the stars. The future of this technology is about taking control of light. We are moving toward an age of massive laser arrays in orbit. These arrays will act as the permanent wind for our deep space scouts. They will fire concentrated beams at ultra-thin sails. They will accelerate them to speeds once considered science fiction. By moving our light sources beyond the air, we eliminate the blur. Our power remains sharp. Our reach becomes effectively infinite. It is a transition from a weak natural resource to a human highway through the cosmos. Every breakthrough has been a necessary step. The folds of our cosmic origami were vital. The reflective efficiency of our polymers was key. The lessons from Icaros led us here. We are perfecting the tools that will allow our descendants to visit other stars. One day, they will look back at our sun as just another tiny spark in the sky. Space is no longer a barrier. It is an ocean. Like the ancient sailors of Earth, we are learning to harness the environment. We are using it to carry us into the unknown. The solar sail is more than just an engine. It is a symbol of our technical mastery. It proves that we can move across the universe. We do not need the heavy burden of the world we left behind. We have become the new sailors of the starry deep. With every photon we catch, we get closer to the edge of reality.